Welcome to another video for organic chemistry. In this video we're going to be discussing inductive effect. So we have here three different species here. We have a 3-degree carbocation, a 2nd-degree carbocation, and a 1st-degree carbocation. Now if you refer back to our previous problem, our problem dealt with the first two on the right. Those were the two options. But there's actually a 3rd-degree carbocation also that we're going to discuss. Okay? Actually, our 3rd-degree carbocation is the most stable. Our 2nd degree is more stable, but not more so than 3rd degree. And then our least stable carbocation is our 1 degree. So let's go ahead and discuss our 3rd-degree carbocation. Let's talk about why the varying stability in each one of these types of carbocations. So if I break down the our 3rd-degree carbocation to its simplest form, you'll notice that the middle carbon is bonded to 3 other carbons. Now let me add on the rest of the atoms that are involved in this particular molecule. Okay, so we got a CH3. All of these are CH3s that are surrounding a middle carbon. Now if you remember, carbon has a maximum of 4 bonds that it can make. Okay, but it has only 3 bonds. So our middle carbon is bonded to these 3 carbons, leaving me with an empty orbital. Okay, that empty orbital gives me a positive charge for that middle carbon, and that gives me a plus charge, and that's where my carbocation term comes from, right? My positive charge. So this positive charge attracts the negative charged particles. So for example, since this carbon is empty, this has an empty orbital and has a plus charge, it is going to attract the negative charges from its surrounding methane group carbons as well. Now, the fact that it has 3 carbon surrounding molecules around it, that gives it more ability to distribute that positive charge, causing it to be a fairly stable carbocation. Now, keep in mind also, as stable as this is, that doesn't mean that it remains that way. That just means that this is the more likely carbon to be involved in a bond with another element. Okay, so that positive charge gets distributed throughout this entire molecule, or you can say that the negative charge, the electrons from the surrounding molecules, are distributed evenly throughout, and this is what causes the stability in this carbocation. So it's kind of drawing electrons from its surrounding neighbors, and it's sharing it, and thus causing it to be more stable with that plus charge. Now actually another term to discuss in this section would be hyperconjugation. And with hyperconjugation, I actually just referred to it in a sense because if you notice the surrounding methane groups, they all have H groups, H elements attached to them. Those H elements have single sigma bonds. Those electrons are being shared between the hydrogen and the carbon. Each carbon surrounding my middle carbon has 3 H bonds, has 3 sigma bonds. Now those sigma bonds, those electrons, are actually helping and stabilizing my middle carbon as well. Okay, so hyperconjugation. So all of those negative charges, all of those negative sigma bonds from my carbon to hydrogen bond, those actually end up sharing some of their negative charge with my middle carbon. So the more methane groups that I have surrounding my positive charge, the more stability I have because of the inductive effect and hyperconjugation. So it's kind of like a neighbor sharing all of its sugar. You know, the more neighbors you have, the more neighbors you can draw from in terms of what you can use. And in this case, we need electrons, we need charge, and we need to distribute that positive charge that's in the middle that's causing an issue in my molecule. Okay, so we have great charge delocalization, it's called. So you're distributing the positive charge, distributing negative throughout the entire molecule, delocalization. So let's take a look now at my 2nd-degree carbocation, which is actually the one that is involved in the problem we had in our previous video. So you'll notice here, this carbon has 2 methane groups that it can share from. Now it is making a bond with hydrogen, but it can't really draw electrons per se from that hydrogen. So I still have an empty orbital, which is giving me a positive charge in my middle carbon. Okay? So this particular positive charge is able to draw electrons from its neighbor methane groups. And when I say methane groups, keep in mind I'm referring to my CH3 molecules. And just like my previous third degree carbocation, the same thing is happening. My inductive effect where my electrons, my electrical charge is being distributed in this molecule, and that positive charge thus, instead of that middle carbon having to take that entire positive charge, causing great instability, it's able to delocalize that charge and cause it to kind of stabilize a little bit more, making it more preferable than a 1 degree carbocation. Now the third degree carbocation is still more stable than this one, again because it has more neighbors, more CH3 neighbors than this one. So hyperconjugation also applies here. You have 2 methane groups surrounding my middle carbon, and then all of those hydrogen bonds, those sigma bonds that are being created by the CH bonds, those sigma bonds, those electrons, that electrical charge, that negative charge is being distributed to my empty orbitals, causing it to kind of stabilize and relax a little bit. Okay? So charge delocalization is occurring here as well. Alright, now let's take a look at the most unstable, my 1 degree carbocation. You'll notice here, that I only have one other carbon species that I'm bonded to, my CH2. So hyperconjugation and inductive effect is still in effect here. I still have an empty orbital that needs negative charge, needs electrons, but I only have one CH group to draw from. I only have one neighbor. Okay. So that positive charge does not get delocalized or distributed throughout as much space as the previous examples, thus causing a more unstable carbocation. So this is not a lot of space for the charge to delocalize, thus not likely to form in a reaction. This is not likely to be the intermediate species in my reaction. You're more likely to get a bond or an element that will react with a middle carbon as opposed to a carbon that's on the outside. Okay? So again, my third degree carbocation is my most stable due to the fact that it has more neighbors, if you will. And going back to my problem, I was dealing with these potential options, and I discussed why the second is the best. My second degree carbocation, it has more CH groups to draw from. Back up. It has more CH groups to draw from than my 1 degree carbocation. Okay, well, thank you for listening. I hope this helped. That was inductive effect with some hyperconjugation thrown in there. Thanks for listening, and good luck in your studying.